you, André, for the introduction. And I would like to thank Zia and the organizers for inviting me to speak at the conference in honor of Professor Yumo's birthday. Even since grad school time, I have been reading lots of papers by Professor Yumo and his collaborators from X type of results and equidistribution results. I also want to thank Zian, a student of Yumo, who has taught me a lot about Yumo's beautiful results and techniques. I have used some of these in my research over the years. I also have overlap with MML during my time at OSSE and at MSI. I really benefit from these interactions. Today, I would like to talk about my joint work with Frank Calegari and Vesselin Dimitrov. Some of you may hear some parts of the talk before, and I would like to say a little bit extra about what we are thinking right now. Okay, but I'll start from the results which has been written in paper. Let me just write down the title. So we talk about so-called the arithmetic power series, and to put it into fancy language is we use Arakelov theory to study these power series, and inspired from the work of Ivan J. and Bost and François Chat, with applications to irrationality. Okay, so let me start from state the theorem. I intentionally state the two results that we have together, as the hope is if one thing you're going to get from the talk today is that these two results are essentially the same theorem. So the first result is if we consider the special value of the Dirichlet L-function associated to the quadratic character with conduct -3 and evaluate 2, this is an irrational number. And moreover, we actually prove that 1, zeta 2, and L2 chi, these three numbers, are Q linearly independent. So any rational combinations of these two are not rational numbers. And the second is we consider product of logs in the following form. So we have two integers. And then we consider the product of log of this particular form. And conjecturally, this should be a transcendental number in general. But our theorem so far can only show that this is irrational. And under the following assumption, so if the ratio of Mn is very close to 1, and actually we give an explicit bound on that. Okay, so it's the goal, of course, would be ideal to prove some irrationality result of product of logs, but this is what we have so far. And slightly more generally, what we actually prove is that this number is indeed Q-linearly independent from each of the factors. Excuse me. Okay, so let me just make some remarks of the theorem. The first thing is related to the first theorem. Of course, if we talk about special values of L functions, the first thing that you may think about is the work of Euler and Dirichlet. So you have class number formula for special value at 1, and then depends on whether your quadratic character is even or odd, then you have full answer about what does the special value look like when this one and that one have the same even or odd properties. And then so it's essentially related to pi and also log of algebra numbers. That's why you can quote Lindemann's theorem, and this will give you transcendence for, as I said, for L k chi, where chi is quadratic character. So for k equals to 1, and for k chi both even or both odd. And then, so if you want to go further, okay, if you want to go further, there's like our theorem, which is the first odd character when you evaluate at 2. And there's also Apres' work. We know about zeta 2, but like zeta 3 is the first odd unknown, like modulo these results, the first like odd number associated to an even character. And Apres proved that this is irrational. And then our work and Apres' work has like relations to each other in the sense is like the general philosophy. Beyond these parts, you have more theory going on. And then what happens here is like there are certain ways to construct rational approximations to the interesting period. And then we want to use those rational approximations to conclude certain irrationality result. Okay. And then I want to make a philosophical remark. So philosophically, you of course could quote Grothendieck's period conjecture. And then for the problem for logs, you particularly have Chenius conjecture. Both of these actually show up in Emil's work, in previous and recent works. And then so basically these two conjectures, which is wildly open, says that you only expect geometric relations from algebraic cycles to give you algebraic relations among periods. So philosophically, things are very clear that all the things that we prove so far are definitely conjectured to be true. But like, unfortunately, things like both conjectures are wildly open, so we wouldn't be able to just quote the result and get something. And now I want to make the remark for the log problem is, of course, if we talk about the Q-bar linear combination of logs of algebraic numbers, and this is Baker's result, Baker's theorem. And then beyond Baker's theorem, there's limited things we know for like product logs, especially when we have like two independent variables. Okay. And then the next remark is the slightly new part of today's talk. I'll make it vague right now, is we can upgrade. When I say upgrade, it means literally we use the same framework. We can upgrade our proofs to give upper bound on irrationality measure. Okay, I'll talk about this in a little bit more details later. And then you just view it, this is like, so far I state the theorem as just a qualitative result about like you have like certain things to be irrational. And then we actually can make it like first step quantitatively using the so-called irrationality measure. And I'll give the formula later when we talk about the idea of proofs. Okay, and then let me just give a little bit overview of the talk. So the proof is we use rational approximations to periods from literature, and I'll give precise references later. And then what we do is like these rational approximations goes to the period fast enough, as in Apres' work, that one can directly conclude the irrationality purely from the rational approximations. And then the new input from our work is like we get inspired by the work of André and also the recent work of Bost and Schock. We make use of not converge fast enough rational approximations. Sorry for put all these words together. Okay, so basically it's like there's multiple ways that you can construct rational approximations, which I'm going to review the 2 examples for our theorem, either using theory of modular forms or using like algebra geometry, which I'm not going to go to detail today. And then so using like Arakelov theory, namely more precisely the Arakelov theory used to prove like arithmetic algebraization theorems in previous work of these authors and others, we actually been able to like try to use some of the like classical rational approximations. Okay, questions so far? So let me just recall the key properties of the rational approximations in literature. Okay, so for part 1, we actually have Sergei's work, where if you read his paper, he first gives you explicit induction formulas on like a sequence of rational numbers, which give you approximations to L2 chi, and which is like of the same spirit as André's work. And then in his paper, he also gives you like module form interpretations of his construction, which is actually inspired by Berkeley's work, who gave modular form interpretation of André's construction. And then, so there's also the work of Varel. And then she gave a geometric interpretation of Sergei's work. Okay, the years is a little bit wrong because I think the like manuscript was around before it was published. Okay, so let me just jump towards like what is the actual properties that we are going to use. So on y0 6, and then this is the modular curve, the open modular curve with level gamma 0 6. And then if we actually pick a Hapton modulo of it, it is isomorphic to P1 minus the cusp given by these 4 numbers. And then this choice is made that actually is like the coordinate here, the integral structure of the coordinate here, match up with the integral structure of the Q expansion. So this is a nice choice of coordinate. Okay, and then what does the construction give you? The construction actually gives you 2 power series. One is z coefficients. The other is rational coefficients, such that the important part is both of them satisfy a linear ordinary differential equation on P1 with singularities contain the actually singularities equals to the set of these 4 cusps. And actually, indeed, this is a 2nd order linear ODEs, satisfy this one. For the homogeneous 2nd order one, this one satisfies the same one, but inhomogeneous. The differential operator is the same. And then the differential operator is actually coming from the Gauss-Manning connection for the universal family of elliptic curve here. Okay, so, and then that's no wonder that you have, you think about them as solutions of vector bundle with connection or just solutions of ODEs with singularity exactly at the cusps. Okay, and then, 2nd order. The second property we have is for the coefficient. This one is already like do not need to say anything more about the periodic property as it's already integer coefficient. And then for the B part is let's use this to denote the LCM of these numbers. And then its square kills all the coefficients. Okay, so far these 2 things has nothing to do with the period that we're interested in. Now this is the third property. The third property says that, okay, if we view this as like horizontal sections of a vector bundle with connection associated to the linear ODE is like, so both of them are regular at 0. And the next question you can ask is, what about the local monodromy at 1/9? Is, of course, each of them would have non-trivial monodromy at 1/9, but the period show up as the factor which kills the local monodromy. So I'll put it in a slightly more elementary way, saying that as a power series with real coefficient, this one has convergence radius equals to 1, which in this case it is equivalent to say that it has trivial local monodromy at 1/9.
It makes sense.
Yes.
The connection.
Yes, exactly.
What is the meaning of this notation just before? The segment 1 to n to the square bn is easy. What does that mean?
This means that the square bracket means the least common multiple of these numbers. And then, so one way to, okay, I'll choose the easy way to say it. The easy way to say it is it's coming from the echelon integral of modular forms. And you do echelon integral twice, that gives you this coefficient.
So is there a singularity at 0?
Yes. But both solutions, so the differential equation of the vector bundle with connection has singularity at 0, but both solutions are regular at 0. Yeah. There are solutions which are irregular at 0. I didn't tell you.
So could you recall what AN and BN is? It's development of the logs?
No, I didn't recall for you what it is. You can read the references. Yeah, so for the purpose of today's talk, this is the important property that you need to know. You don't need to know what explicit these things are. You can read the explicit formula from Zaghi's paper.
Okay. What is the definition of AN? What is the definition of HA, HB?
Okay, so let me emphasize again, for today's talk, you just need to know that Zaghi constructed these functions with nice properties. And the definition, one way to do it, this coming from the, okay, this coming from X is the half modulo, this coming from the some modular form, and this coming from the product of some modular form and some echelon integral of some other modular forms.
But for a second order ODE,
yes.
Just, so the space of solution is two-dimensional.
So this is homogeneous, this is inhomogeneous. So actually, in total, if you put together, and if I want to make it homogeneous, it will be rank 3. So I actually have another solution which is not regular at 0. Does that answer your question? So I have a linear operator of order 2. Let me denote by L. So we know L HA equals to 0. And what we know is L HB is equals to 1. Okay. Yes?
And there is another thing, can I ask?
Yes.
So that's a power expansion
yes.
at 0?
Yes.
But you were talking on the monodromy at 1/9.
Yes.
So
1/9 is, one way to see it is 1/9 is another cusp, and you have the Artinella involution relates the two, and then you can use certain transformation property of modular forms to see that this is the factor which shows up there. Okay, other questions? Okay, good. So yes, so doesn't matter how much you know about modular forms. These 3 properties is the only thing that we are going to use. Okay, so now I'm use the second half of the Bible to tell you what happens for 2. And there are some constructions, but in the end of the day, it doesn't really matter for us. The properties are what matters. So how do we do it? Okay. So first is there's one good thing about the product of logs is that we have good rational approximation to log. You actually could use the same way to prove, okay, of course you have Baker's theorem, which kind of apply to all the cases. And, but if I just want to have an elementary proof of these one of these log factors that I wrote down to be like irrational, you can just actually mimic Apres proof. You have nice rational approximations to these logs. And then so one easy thing, actually, let me just give the reference in case you want to look it up. So you can either look it up in R.D. Robinson's work, and not surprisingly, as I said, it's like you can use similar ideas as Apres, so you can find it in various papers by Van der Putten where he reinterprets Apres proof. Okay, so basically you have rational, this gives you a good rational approximation for, let me just say for log 1 plus 1 over m. Of course, it works for a more general setting. And then so now I want to have like a rational approximation for the product. I just take the product of the rational approximations that for each of them. Okay, and then let me just make a remark here. It's like what happens here if you rewrite this one. So this line would actually tells you that the limit of bn over an is actually equals to the period here. So this is where the rational approximation coming from ratios of these two generating series. And then so which means it's like in both R.D. Robinson and Van der Putten that you actually have like two power series, and the ratios gives you the log values. And then we want to take the product of the coefficients, and that's the algebra product of like power series. Okay, so let me just write this sentence down, is that we take so basically, it's like each of them, you have a corresponding A type of sequence, and you have a corresponding B type of sequence. You take the product of each. And then you can deduce the following properties that we have still. We have a power series with Z coefficients and a power series with rational coefficients. Everything is on P1, such that P and Q satisfy a second order linear ODE on P1 with singularities 2. So you have 0 and infinity. That's a property for algebra product, is that you have 0, infinity, and the product of corresponding singularities for each cases. So where alpha m and beta m are the two singularities corresponding to a plus minus a square minus 1, where a equals to 1 plus 2m, and then similarly we have the two singularities. So these are actually the two singularities for the like generating series of the single logs. Okay. So this is the first property, that we have control of these singularities. You don't need to know what precisely they are. I'm going to give you an upshot in a minute. And then I'm going to copy the second two properties. It holds the same, is that we still have this factor to kill the denominator of the nth coefficients of Qx. And then we also have the period show up. is convergent at alpha m, alpha n. Okay, here is like, let me just say we may assume mn are positive. If not, you can use the log rule to change them. And then so alpha is the smaller roots, beta is the larger roots. We have is like this particular period will kill the local monodromy as the singularity nearest to 0. Okay. So let me just summarize. Is like what happens is like one way to understand the classical rational approximation in Dirichlet, that's actually how people write it. They call it a priori limit. Is just the saying that we have power series or horizontal sections of like a vector bundle with connections, and we have certain control of the denominator, and then we have a particular linear combination where the period show up such that it has trivial monodromy at the singularity nearest to 0. Okay, now I'm going to just summarize. Let me just actually write down what I said. So the upshot is now you can forget about like all the detailed property, but focus on this one. So if we assume the proof will always coming from assume for contradiction that the period, and I'll just focus on the proof of the first part without the moreover. The moreover part can be proved using like very minor modifications of the method. So we assume this is rational, or we assume the product of log is rational. And then we get, let me denote each of them with a letter. So I'll denote this one with h1x. And this one with h2x. So we get, so I equals to 1, 2. hix is a Q coefficient power series with the like assumption for contradiction. And then it has the property that we have some control of the denominator, Q's nth coefficient denominator. And then we have that, so hi satisfy a second order linear ODE on P1 with singularities contained in these 3 disks around 0, 1, and infinity. Epsilon is some small number. Okay, you probably feel like 1/9 is not very small, but in practice for our like numerical computations, it is small. So you can just think about epsilon as a small number. And then the third property is that it is as a real, okay. This is actually, yes, with respect to real metric. And so this is all with respect to real metric. Okay, so this is actually convergent on the small disk around 0. Namely, it extends over the first singularities here. And then we may actually, so if your epsilon is like well chosen, we can say so does hi use the substitute, because when I state it this way, is that 1 and infinity are symmetry with 0 fixed, and hence it's like if I do a substitute of variable, the same thing will still hold. Okay, so this is all we need to memorize for these properties. And then the first thing I want to remark is,
so it doesn't exactly kill the denominator because you assume something.
Yeah, so up to a constant, you're right. So up to a bounded constant which doesn't affect our proof. so let me just say it's like, is it okay if I write on this blackboard? Okay, so I will say it's like, what happens to every case? Why things works there, why things doesn't work here? So comparison to. Sorry?
For H2, you have other singularities. Here you put singularities at 0, 1, and infinity.
Containing the small disk around the 0, 1, and infinity. Sorry. So here's the part, is that let's, hopefully I understand the question correctly, is why is H2 satisfy the property that I wrote there? So here's the part, is like recall our, I should have that. So we have this condition, very small. I'll just say very small. Okay. And then this will imply that A over B minus 1 is very small. And then which says that, so actually it's like these two things are very close to each other. Those two things are very close to each other. And the product of these two numbers is 1. And hence it's like this is very close to 0. This is very close to infinity. Both of them are very close to 1. Thank you for the question. I should have said that. Yes. Okay, yeah, this is where we use the extra condition in our theorem. So basically, it's like if you can come up with some other ways to construct a like generating series with nice pattern of singularities, then you can actually extend our proof to other settings as well. Okay, so yes.
Yes, I have a stupid question, but could you recall what P and Q is and what the
no, I didn't tell you what P and Q is. So here's the reference that you can read. And then this is the property that they have.
Okay.
Yes.
So I don't remember the classical result transcendence, but if you just take log of a rational number,
yes,
you know that this is transcendent.
Yes. Yes.
Okay.
Yes. Okay, so yes, so basically it's like in order to prove it is transcendence, you have Baker's theorem, or the more classical you have like Lindemann's theorem. But we are doing a different way in the sense it's like you can do it in the a priori way that construct, if I'm happy with irrationality, you can construct a rational sequence and then which goes to the number fast enough. And that's what happened in these two papers. And then we're going to borrow that from them. Okay, so let's say it's like why a priori. So far it's like everything sounds exactly, if you ever seen a priori's proof, everything sounds exactly the same. It's like why people who come up with these rational approximations didn't conclude they are irrational. So here's what happened, is in a priori's case, is he has like y1 plus 6, and this one is that it has 0 infinity as cusps, square root 2 plus minus 1 to the 4th as elliptic points. And then he has ax, bx, similar to the ab, pq above. And just as like we have bx minus zeta 3 times ax is actually has convergence radius equals to the large elliptic points. So each of them is only converged to the smaller elliptic points, but this particular linear combination kills the local monodromy there, and then you extend to the larger one. Okay, and then, so the thing is like, so I'll state it as an easy fact, is there is no non-polynomial power series in Qx with convergence radius at least this number and denominator killed by 1 to n to the 3rd power. This easy factor coming from the easy numerics that the log of this number greater than 3 and the plus prime number theorem. Okay, so basically it's in every case, it's like if we assume for contradiction this is a rational number, then it is a power series which has convergence radius this number, denominator killed by that number, which must be a polynomial by the easy fact. And by the construction, you know it is not a polynomial. Hence, you get a contradiction. And so this gives you the contradiction. But if we look at our case, so our case, of course, I can write for you a power series satisfied above 3 conditions. So for instance, I can take log 1 minus x. This is sum of minus xn over n. So it's the n kills its denominator. It satisfies, of course, it satisfies second order differential equation because it satisfies a first order differential equation. And then it has convergence, it's convergent in the like disk around 0. Okay, so this is actually a function which satisfies the above 3 conditions. So it's not that easy that we can just conclude as a classical situation that it is irrational. So, and what actually happens is like you can translate this property to how fast the convergence rate of this rational approximation. And then this kind of like, this property of convergence radius and the denominator just exactly like describes like the rate of convergence. And then in our case, it's not fast enough. Okay, but like you do not stop there. Because it's like, let me ask a question, and actually that's kind of how we get inspired from André's work, is, yes, I'll give you an example which satisfies the above 3 conditions. And then the first question you may ask is like, can I write out infinitely many power series? Okay, by infinitely many, I mean QX linearly independent, otherwise I can do like linear combinations. So can I write out like infinitely many of these examples? The answer is no, and there's hope. Because it's like, if you know what are all of them, and then you see it's like they are not your HIs, then you actually win. Okay, so this is what we do. Okay, so one thing is that when I write these names and I mention Arakelov theory, then you know for sure that everything works for like number field, and everything works like every places works the same. You can work with Archimedean place, non-Archimedean place, and also it doesn't necessarily need to be P1. You can work with like any curve that you want. But like for the sake of time and for simplicity, I'll just talk about the simple setting in our case that we just work with Archimedean place and using the integral structure to control the non-Archimedean places, and we work over Q. So the setup is the following. Is we are given sigma in a positive integer, a non-negative integer. So in our case, we'll have sigma equals to 2. And then we have another thing, which is a little bit hidden. So phi, which is a map from the closed unit disk to C. This has coordinate x, such that 0 maps to 0, and the derivative at 0 is not 0. So you can, the easy way to think about it is as a like substitute of variables, which kind of describe for you the convergence property in Archimedean place. Let me say it explicitly here. So what we'll consider is we consider all the power series Fi. So I assume just some index you can ignore. What we say is like we just want to consider all the possible functions which are rational power series. And then we have some control of the denominator. And we have some control of the Archimedean place. So when we pull back Fi using this change of variable, it is meromorphic on the open disk is good enough for our proof. Okay, so it's like I already spoiled her. I said that for this particular setting, we're going to have a finite dimensional vector space. What are we used here? So it actually goes back in André's work, which he tells you the following. It's like if we have the log of the derivative at 0 of this phi function greater than sigma, then the qx span of these fi functions is finite dimensional, which is smaller than an explicit bound in terms of phi and sigma. Okay, so what actually happens here is like if I think about everything in like adadically, this is like some part we have some control about like denominators, namely the finite contribution. We also have some control of the Archimedean part. And then, so because we have z here, so you don't see any finite contribution, but this is essentially the degree of some like Hermitian line bundle associated to your problem. And then this is a positivity of degree condition. And that's why in classical like formal geometry type of thing, when you have a positivity or ample line bundle, you will expect a finite dimensional type of results, which you can find more geometric interpretations in the paper by Bost and Shaw. Okay, so explicitly in like André's work, he already gave you an explicit bound in terms of phi and sigma. Okay, so let me just I'll tell you what the bound is in a minute, but let me just tell you, it's like we already see sigma is a 2 here. And then you can think about what phi you want to pick in the following sense that, so we have a differential equation, and then you just want to choose some nice change of variable so that your formal solution will be convergent on the disk. And one thing you could do is pass to, for instance, the universal covering. And then these are the type of things that one can do here. Okay, so I'll give you more details on the choice of phi, but let me just continue this discussion and tell you, it's like, okay, so when I put it this way, it's like you feel it's like, oh, we can just stop in last century, but we cannot. The reason is that the bound was a little bit too large. And to actually being able to pin down what, if I go back to what I said here, is like, if you can actually pin down all possible functions here, then you have a chance to win as in the classical case. Okay, but this bound is a little bit too big, so we wouldn't be able to find that many functions there. Excuse me. And then so basically it's like in our unbounded denominators paper that we actually give a first improvement to this bound, which was like not good enough for the theorem here, but good enough to solve the unbounded denominator conjecture. And around a similar time, there's the work of Bost and Shaw, which actually our later work is built on. They actually gives you a better bound than what we did in our paper. So we still need to have the same assumption. So this assumption needs to be there for all the situations. And then what their bound is the dimension. Let me just say the dimension is bounded by, I'll give you the explicit formula because later I want to talk about irrationality measure, and then you'll see, like, hopefully even from just reading the formula, you can see that it should be essentially the same proof. Okay, so we have like unit disk, hard measures, and then we have integral of this particular form. And this, when I written this way, it's not very like illuminative what it is, but actually you can see the work of Bost and Shaw. They give you, this is some self-intersection number of an Hermitian line bundle associated to phi. And then this is actually certain like arithmetic degree of tangent bundle. Okay. And then so you actually have geometric interpretation. The things I put it this way, it's not surprising that you actually can do it like beyond P1. Okay, so that's already a good improvement compared to our work. And then what we did is, I'll just put a color chalk so that I don't write a big formula, is that we have some denominator improvement. And then we also have minus something. And something that we call it convexity improvement. So actually, if you look at the work of Bost and Shaw, it's like their bound is sharp in general. In a sense, it's like if your phi is injective, the bound is actually quite sharp. But then in our practice, as I said, we're going to like convergence radius is not good enough for us. We want to take, for instance, like universal coverings. So those maps are like in general, not injective, and hence that we can actually do some improvement, like which we call it the convexity improvement related to. There's some interpretation using Navina theory, which I'm not going into details. And okay, so basically it's like there's certain improvements of the bound. And I also want to make a remark saying that we also have some slightly weaker variants, but computer friendly. I have to be honest, we use computer in our proof that in the end of the day, we need to compute a bound, which I'm going to tell you in a minute. And this integral has like a series like singularities. So like to compute its integral to the regulars that you want, it requires a little bit of work. And we give some approximation, which we proved is weaker than these bounds. But like in practice, like you can also use them to prove irrationality. Okay, so this is just a like upshot. Upshot is like the setup is you have some control on the coefficients integrally. You have some convergence property. You can get a dimension bound. And let's see how we actually use it. So the application we take, so let's just do the easy case that if epsilon equals to 0, then we can take modulo closed disk, open disk little issue. Then we can take phi to be the Q expansion of the Legendre lambda function. Because this is the unique function which is like, it's a universal covering away from 0, and it has a unique preimage of 0. So that's the universal property that you can actually use to characterize such a function. And then, so if epsilon is 0, then we can see it's like lambda.
You said delta, you said d bar here.
Yes, I say modulo that little issue. As like you could see from the formula, you just shrink a little bit. It shouldn't change your number too big. Okay, so then we would have the pullback of these fi. So actually, what did I say? Hi to be convergent on D. And then let's check if the numeric condition holds. Is we actually have that the log of the derivative of lambda at 0 is log 16, which is greater than 2. That's nice. Okay, so for all I talked about, let me go to the simple setting. Is we have certain things which, essentially speaking, the convergence radius is 1. And the 1 is too small for this a priori classical thing to work. And then we use a boost using the like a lambda function or whatever kind of like covering map that you want to have associated to your differential equation. We have a boost by 16, which explained why like all our theorems have like this denominator 2 type of like conditions. So you need some extra work if you want to go to the next step 3. Okay. Okay, then let's just let me quickly finish this one, and then I'll talk a little bit about the irrationality measure. So okay, so what happens is like for our epsilon is like we can shrink d a bit, because it's like geometrically speaking is if this is the disk and then we have the lambda map, and then all the pre-images of the disk around the 0, 1, and infinity would be along here, except the one in the middle, but we don't need to rule that one out because we have the condition that it is convergent on the like small disk around 0. So that's why you don't need to rule out the unique pre-image of 0 in the middle. So you just need to rule out these things along the cusps. And then so you don't need to move out things too much, and then pick a simply connected domain, make it isomorphic to like the like closed disk. Okay, so then it's like we actually get, so I'm going to lie a little bit. We get upper bound dimension strictly smaller than 9. And then on the other hand, what functions do we have? We have f1 equals to 1, f2 equals to log, f3 equals to log square, and f4 equals to li2, f5 equals to this iterated integral, which you can actually realize as some hypergeometric functions. And then we have our f6 by assume for contradiction we have hi and the hi derivative. These are linearly independent because they satisfy a second order differential equation. And then we can also do change of variable and its derivative. And this gives us the contradiction, because it's like on one hand our upper bound is smaller than 9. On the other hand, assume for contradiction we actually has 9 functions. So which means it's like these functions shouldn't exist. And hence the period should be irrational. Okay, summary. What happened is the following, is that you have a rational approximation which is not good enough, namely this is not working. And then that's why it's like you want to boost your convergence radius. And we boost our convergence radius using like André's work, saying that you just need to do a substitute. And then you can actually have a better chance to boost your radius to beat your denominator. So that's step number 1. You find a nice kind of phi, which usually based on your property of the differential equation, and then such that this positivity condition holds. And the second is like, unfortunately, in the previous case, you just stop because all these generating series are usually obviously not polynomials. But like in this game, you usually actually has a positive dimensional vector space here. And then what we do is just like you adjust your phi so that you can get a good dimension bound, which is sharp enough in the sense is like here we have like 5 honest functions plus like 4 ghost functions, which means that your error is kind of 4. It's like if you can actually beat anything which is smaller than 5 honest functions plus 4 ghost functions, then you actually prove that these ghost functions should not be there, and hence your like period is irrational. Okay. And then so
how do you know they are independent?
Yes, that's a good question. Is that one easy way to, okay, by easy, it took us some, what we actually did first is you think it must be a finite dimensional question, so you ask a computer program to verify their first coefficients are not linearly, like are independent when you truncate to say x to the 100. And then, so once you know for sure they are not, then you can go prove them by verify local monotomies. The local monotomies of these differential equations, because these are the honest functions, you know what they are. And these ones is like, although I didn't tell you what they are, but okay, they are explicit and they satisfy the differential equation, so you can actually use the differential equation to compute the local monotomy. And then it's like, it's a if and only if, because these all things that happens here has geometric nature, so they have regular singularity. That's why it's a if and only if condition. On P1, when you verify all the local monotomies are trivial, it must be like polynomial on the base. So you can actually, like once you are pretty confident that these are linearly independent, then you do a local monotomy computation to show that they are actually linearly independent. Okay, other questions? Okay, so that's the, use the next blackboard. So, what can we say about irrationality measure? Okay. So it's like, let me just state it. Assume that we have an infinite sequence of rational numbers such that, let me just say for alpha you can plug into the elements that we have, such that it has smaller than 1 over q to the n to the kappa. And then, so which means it's like, if we can give a bound on for which kappa you may have infinitely many solutions, or like, yes. Okay, then you would actually get a bound for irrationality. Let me just write it down so that we can see it. So this Pn, Qn, let me just say non-zero integers. Okay, so with the same phi and sigma as before, so if we have an infinite sequence, then we have the dimension over Cx of all these Fi's that we used in our proof of irrationality measure is smaller than still the double integral and then still the positivity condition. And then this is what comes in, is like you have rho where rho equals to the minimum of absolute value of the preimage of singularities. Okay, so basically you have a bunch of singularities, and you have your map phi. You pick the like smallest, you take the preimage, pick the element with the smallest like absolute value, and put it here. And then this is the extra term that you get compared to the dimension bound. Okay, in the sense it's like for the whatever I written in yellow will actually carry through here. That's so. What does it actually say? It says it's like, we know, okay, so if we have irrationality, then we actually have is like this number is smaller than that. That's how we conclude our irrationality proof. And then now we say, if we have a sequence with respect to this like kappa, and then the kappa must satisfy this condition. So which means this formula indeed gives you, so this actually gives you, if you translate in terms of the definition of irrationality measure, this gives you an upper bound on irrationality measure. Because it's like when your kappa goes to infinity, this goes to 0, and then this inequality will not be satisfied based on our previous discussion when you already have irrationality. That's why it indeed gives you an upper bound of kappa, which you could have a sequence of infinite like rational approximation being that close, and hence that gives you an upper bound of the irrationality measure. Yeah, the logic is a little bit like involutive, but like let me just say the upshot is like this formula, the kappa actually gives you an upper bound of the irrationality measure. And let me just stop here. Thank you very much.
Thank you very much. Some questions?
Do you think you can apply this technique to get some bounds for the irrationality measure of pi?
Yes, we can, just haven't yet beat the current record. Yes. Okay, since Javier asked this question, let me just say something. Is that so if you unwind everything to the injective setting convergence radius, this factor of 2 is the part which kind of we are off by the classical method. So the classically, if you have this convergence type of like result, you have a formula, say in Nestorenko's work or other people's work, that you get the irrationality measure. But we are off by a factor of 2. We do have some improvement in our settings, but not yet beat the total. Like we have some little improvement, but not yet beat the whole factor of 2. So that's why it's like the bright side is we do give an irrationality measure for whatever our method can prove irrationality, but we do not recover the like the most classical one. So we haven't yet beat the record.
Sure. Yeah.
Is there a geometric interpretation to this series?
To you mean this power series? Yes. So the thing is like, as I said. Okay, I'll first give a reference. You can read like there's various paper by Matt Kerr, Kerr, and his collaborators, where he talk about like. So I think he probably even started from anyway. He have lots of like. Geometric families using like intersection cohomology to like give you like interpretations of these differential equations type of things. And then, but concretely speaking, in this case, it's just nothing. The homogeneous one is nothing but the Gauss-Manning connection, and then the other one is usually coming from just an extension of the previous case.
So
the inhomogeneous one.
It's a Gauss-Manning connection of what? So what is
the universal family of elliptic curve? Yeah.
Yeah, and since the phi you choose is also universal elliptic curve, that's a
yeah, but that's not the same universal.
So it's not the same, but can we find a system why is the two? I mean,
not yet. Yeah, that's a great question. So we haven't been able to. So yes, that's a great question. That. The unfortunate part, okay, is that this has a geometric interpretation. Yes, that phi has a geometric interpretation, but it's not the same geometric interpretation. And we would like to have a better kind of way to understand what are the best choice of like phi. Yeah, that's not yet.
Yes, please.
What about the number like zeta of 3, where zeta is the Riemann zeta function?
Sorry, what about the number?
The number zeta of 3, for example. I mean,
this one?
Yes. Zeta of 3.
We're talking about zeta 3. Did I misunderstood your question? Oh, whether you can get a irrationality measure? Yes, you can. Just I don't remember what's the number. Yes. Yes.
Do you have a heuristic to predict which kind of number you can prove irrationality by the method? What are the limitations?
The limitations, yes. Okay, so the limitations is the following. It depends on how much you are going to use the differential equations. So far as like, if I'm jumping to the world of p-curvature conjectures, and then you feel that we're just using half of the proof, namely the proof of the like solvable case, which goes back to Tchaikovsky, André, and Bost. That's how we actually use the like, and then they use like universal covering. We essentially also use universal covering and use like the algebraization theorem framework to do it. But we didn't use anything of like Adam's work on p-curvature. And so basically you feel it's like, here's the part. The dream would be if you can use more about the differential equation, then that'd be great. But so far we haven't yet. And then so far it's like, it seems that what we use is just like certain universal coverings. And then for universal coverings, there's always like a finite boost that you can have. For instance, it's like if you have 3 singularities, modulo the small ones around it, it doesn't affect you numerically. So in this 2 example, we essentially have 3 singularities, 0, 1, and infinity. And then you can boost a factor. Okay, 1 can be any number. Then you can boost by a factor of like 16, because you pass to the lambda function, give you the factor 16, while the convergence radius equals to 1. So basically, it's like, for whatever not fast enough, but not too bad, like within the log 16 range, then you can apply our method. And then if you want to go beyond that, either you use more of the differential equations, or some heuristic would be that you want to use convergence, you want to like use 5 for more than one place if you can combine the data together. Yeah.
Yes. So I think the next lecture is at 11:15, so maybe you want to ask a question before we close the session?
I'm good. Thank you.